Hello and welcome. Today we are doing Lesson 8 for our Math 254 Vector Calculus series. Our topic for the day is partial derivatives. We're going to start with some introduction and definitions, essentially what a partial derivative is. If we have a function of multivariables, then we may want to have the derivative of the output with respect to just a single input. What that means, how it's applying to different graphical applications, and we'll get into more of that in the next lesson. We'll look at just how to compute these partial derivatives, and then we will see how using partial derivatives is useful for implicit differentiation. All right, let's go ahead and get started here. So our goal over the next two lessons is to come up with a linear approximation to a function in two variables at a given point. In other words, what we're trying to do is find the equation of a tangent plane. If we think about a function in two variables graphing as a landscape, then a linearization of the surface will be a tangent plane as opposed to a tangent line. We do not now have a single slope, but different slopes depending on the direction being traveled. Looking at figure 8.1 below, 8.1.1, we see that if you travel along the surface in the x direction near point A, you will be on the red tangent line labeled t sub x of AB. But if you travel along the surface in the y direction near this point, you'll be on the green tangent line labeled t sub y of AB. So here in our picture we have the red line. This is our tangent. This is our tangent line, which has a slope in the x direction, and the green line here is the tangent line which has a slope going in just the y direction. So x does not have any change here in the red line. The y does not have any change. Just add, that's a typo, 8.1.1. So figure 8.1.1 is a graph of a surface with a tangent plane and tangent lines in the x and y directions. We can view this at GeoGebra here, https://www.geogebra.org/3d/BVV8JQJP. I'm not sure if I have to read all of that, but the best practices say that I am to read everything on the screen, so I'm going to do my best here. In order to find the equation of the tangent lines and tangent plane, we need the slopes of the tangent lines in the x and y directions at the point A equals parentheses A comma B. Let's begin with the following definition. All right, so essentially, let's just kind of redraw this. If I have some surface here, then, and we're looking at a point here, we can have the slope in the x direction, and we have a tangent line. And so this slope here, we're going to call f sub x. And this point we're calling a comma b. So this is f sub x of a comma b. The definition for our slope is from our first term calculus. Given a function f in two variables, then f sub x of ab equals the limit as x approaches a of, big fraction bar, on top f of x comma b minus f of ab. Oh, here, goodness. Yeah, no, that's right. So the y value we're holding constant at b, while the x is a variable that is approaching a. This is all over x minus a. So b is held constant here, so there's no change in y. But the x is able to approach a from both sides, and this is our slope function. This is the change in our outputs, our change in our z values, over our change in our x values only. So this gives us our rate of change in just the x direction. Similarly, our rate of change in the y direction, given function f, is f sub y of AB. I'm going to switch colors here. So we've got green. So in the y direction, I can draw another slope. This has slope f sub y at AB. And this is defined similarly. The limit as y approaches b of big fraction bar. On top we have f of a comma x minus f of a comma b all over y minus b. Note that the x value is held constant at a, so there's no change in our x value. This should be a y. All over y minus b, and I will fix that in the notes as well before you guys see it. Okay, so that's our slope in the y direction. So these definitions are great, they are true, they work, but they aren't very practical. So we're going to kind of work our way down here and eventually get to how we're actually going to compute these partial derivatives. So these up here essentially are our partial derivatives at the point AB. This is the partial derivative with respect to x, and this is the partial derivative of our function with respect to y. And these allow us to find the slopes in the x and y directions. Instead of finding the slopes in the x and y directions, the partial derivatives at a single point, we're going to find the partial derivative functions and then plug in a point a comma b into that partial derivative function in order to find it. So we'll start with how we are going to define the partial derivative functions. Given a function f in two variables, we take this partial derivative right here, this partial derivative with respect to x of f of x comma y. So this is not our normal d over dx. It's now a delta over delta x. So this symbol here, this delta over delta x, this is now a partial derivative. It's indicating that we are keeping any other variables considered to be a constant while we take this derivative. So the partial of f of x comma y with respect to x, make sure you know how to read that. That's how we are going to read that. This equals f sub x parentheses x comma y. This is our common notation. This here is our Leibniz notation, which we are going to use plenty of as well. And this equals the limit as h goes to 0 of f parentheses x plus h comma y minus f of x comma y all over h. So as h goes to 0, what we're seeing is that our change in x, right here, x plus h, this goes to 0, or this goes to just the same x as what we have over here. As h goes to 0, this goes to 0, so this becomes f of x comma y minus f of x comma y over h. This is the definition. This is compared to, here we go. If I have y equals f of x, then dy dx equals the limit. I want more room here. If y equals, then f prime of x equals dy dx, in our Leibniz notation, equals the limit as h goes to 0 of f of x plus h minus f of x all over h, right? That's our original single variable calculus definition of a derivative. So here we're doing the same thing for our partial derivative with x, with respect to x. We just have the plus h on the x and not on the y. So this is a new function in x and y called the partial derivative of f with respect to x, and outputs the slopes of f in the x direction for any given point in its domain. Similarly, we can say that the partial derivative with respect to y of f of x comma y equals f sub y of x comma y, this is the partial derivative of f with respect to y, equals the limit as h goes to 0 of f of x comma y plus h minus f of x comma y all over h. So again, we now have our change in y is h, change in y, while the x is not changing all over our h, so our change in y is going to 0. So this is a new function in x and y called the partial derivative of f with respect to y, and outputs the slope of f in the, see, this is what copy and paste gets me, in the y direction for any given point in its domain. Okay, but all this really means is that if I want to take the derivative of a function f of x comma y, so a function in two variables, all we need to do is, if I want to take the derivative with respect to x, the partial derivative with respect to x, then I just think of y as a constant because we're saying that there is no change in y. So let's take a look at the following example. Example 8.2.1, given f of x comma y equals x to the fourth plus x squared times y minus 2y squared, find the partial derivative of f with respect to x of 2 comma 1 and the partial derivative of f with respect to y at 2 comma 1. Interpret these values as slopes. Okay, so let's do this. If I want the partial derivative with respect to x, I take this and I just say, okay, x is a variable, y is a constant, so x to the fourth. The derivative of x to the fourth is 4x cubed. Here the derivative of x squared is 2x, and I do not have to use product rule because y I think of as a constant. I think of this as a constant y times x squared. So I bring the 2 down, I get 2y times x. Over here, I think of y as a constant. This is all a constant when we're taking the derivative, the partial derivative with respect to x. So this just goes to 0. This goes to 0 when taking the derivative with respect to x, the partial okay. Then I can say f sub x at 2 comma 1, this equals 4 times 2 cubed plus 2 times 1 times 2 equals 2 to the third is 8 times 4 is 32 plus 4 is 36. All right. Now if I'm looking for f sub y, I now think of x as a constant, so x to the fourth goes to 0 because it's thought of as a constant. When taking the derivative, the partial derivative with respect to y. Okay, so that goes to 0. Here I think of x squared as a constant, y as a variable. So if I'm taking the derivative with respect to y, then this just becomes y. The derivative of y is 1, so we just get x squared here. Minus the derivative of 2y squared is 4y to the first, right? The 2 comes down, multiplies by the 2, we just get a 1. That's it. That's my partial derivative of f with respect to y. So f sub y of 2 comma 1, this equals 2 squared minus 4 times 1, this equals 0. So if we are going to interpret these, we say the slope of f at 2 comma 1 in the x direction is 36, and in the y direction is 0. And that's it. All right. Moving on, let's give you guys a chance to do one. Now you try. Go ahead and work this out on your own. Pause the video, and I will write up the solution and run through it with you in just a couple of moments. All right, and we're back. So let's just run through the calculations here. Exercise 8.2.1, given f of x comma y equals the arctangent of y divided by x. Find the partial derivative of f with respect to x of 2 comma 3 and the partial derivative of f with respect to y of 2 comma 3, and interpret them as slopes. So the first thing that we need to note is just remembering that the derivative with respect to u of the arctangent of u, this equals 1 over 1 plus u squared. So if I have the arctangent of y over x, I'm going to have to use chain rule here because we have an inside function. So the derivative of the arctangent is 1 over 1 plus the inside y over x, quantity squared, times the partial derivative with respect to x of y times x to the negative 1. I've rewritten y over x as y times x to the negative 1 so that I can quickly, easily take the partial derivative with respect to x. So the partial derivative of this with respect to x is negative y x to the negative 2. So I've written that now. I've put that on top of our fraction. So we have equals negative y x to the negative 2 over 1 plus y squared over x squared. I then take this x to the negative 2 and I push it onto the bottom, and it goes to both of these terms here. So I could also think of this as multiplying the top and the bottom by x squared to clear out that x to the negative 2, and we get equals negative y over x squared plus y squared. So if I want the partial derivative with respect to x at 2 comma 3, we plug in 2 and 3 in for our x and our y's in negative y over x squared plus y squared. We get negative 3 over 4 plus 9 equals negative 3/13. So this tells us that the slope of f in the x direction at 2 comma 3 is negative 3/13. Great. One more time, but now in the y direction, the partial derivative of f with respect to y of x comma y equals 1 over 1 plus quantity y over x squared times the partial derivative now with respect to y of 1 over x times y. I rewrote y over x as 1 over x times y, so I can think of 1 over x as a constant and y is our variable because we're taking this partial derivative. We're holding x constant when we take the partial derivative with respect to y. The partial derivative here with respect to y is just 1 over x. So I take that and I push that x across the bottom. So this equals 1 over x plus y squared over x. I then multiply top and bottom by x and get equals x over x squared plus y squared. If we want the partial derivative of f with respect to y at 2 comma 3, we plug 2 and 3 in for x and y respectively, and we get equals 2 over 4 plus 9 equals 2/13. So the slope of f in the y direction at 2 comma 3 is 2/13. Okay, we just want to run through some notation here. So we write a lot of different notations for our derivatives, partial derivatives, and we just want to look at if I have a function f of x comma y and it outputs some z value, which is really what we're going to be looking at, right? Our z values are giving us the height. If I have an x and y value in a plane, then I can go to that x comma y value in the plane and then output a z value gives me that elevation at that location. Sorry, I got interrupted there. Where was I? Suppose z equals f of x comma y, then we define the following notations. The partial of z with respect to x equals the partial with respect to x of the function f of x comma y, which we write equals f sub x of x comma y, and we read this the partial of f with respect to x. Similarly, we can have the partial of z with respect to y equals the partial with respect to y of f of x comma y equals f sub y of x comma y. So it's important to note the difference between the partial of z with respect to x versus the partial with respect to x of z. So this is the partial derivative. Scroll that way. Derivative. We would write partial of z with respect to x equals, say, I don't want to say this. And it would be some expression, so it could be x squared y minus 2yx, for example. And this is the partial derivative function. However, if I write the partial with respect to x, this is a command. This is an operator. I'm operating on whatever is in front of it. So if I have x to the third y squared minus 2xy, this is saying take the partial derivative with respect to x of this expression. It's operating on whatever we have in parentheses to its right. So here this is saying take the partial derivative up here where I have the partial derivative with respect to x of z. It's saying take the partial derivative with respect to x of my function z. Okay. Moving on here. We have these notations. These are our second partial derivatives. F sub x, parentheses x comma y, f sub y, parentheses x comma y, f sub xy, parentheses x comma y, and f sub yx, parentheses x comma y. So the first two are pretty easy to understand. We're taking the partial derivative of our function f with respect to x twice. So we take the partial once, we get the partial of z with respect to x, and then we take the derivative, the partial derivative of that with respect to x, which means we get the second partial derivative of z with respect to x squared. So note that we square the partial symbol here, we square the x symbol down here. This is essentially like saying that we have it's a partial of x squared. This partial is saying that we're doing the partial twice. Similarly, for the partial derivative of f with respect to y twice, we take the partial derivative of z with respect to y, and then we take the partial again with respect to y to get the second partial with respect to y squared. Okay, this gets a little bit more confusing down in the next one, but it's not too bad. We have the partial derivative of f with respect to x and then y is how we read this. So x first, y second of x comma y. This equals. So we're supposed to take the partial derivative of z with respect to x first and then take the partial with respect to y. We would then write this the partial squared of z over partial of y times partial of x. So these we think of as objects. Actually, these are the differentials with respect to x and y, which we will go into formal definitions of those in a couple of chapters. So if we have then f sub yx of x comma y, we're saying take the partial with respect to y first and then with respect to x. So we'd say the partial of z with respect to y and then operate on that with the partial with respect to x. And missing an equal sign. Let me make note of that. We would write the partial squared of z over the partial of x, partial of y. And so when we read this, in this notation, this happens first, and then this happens second. And this is like function notation. If I had, say, f of g of x, I'm doing the function g first and the function f second, and that's because we have this partial insight here with respect to y that happens first in these parentheses, and we're operating it on it with the partial with respect to x on the left here. So we write it in that order in this case, but over here, when I'm using the subscript f sub yx, we're saying do y first and then x. It can get a little confusing. Double check your notes if you're feeling like you're not quite remembering which order to do that in. So we will investigate the second partial derivatives defined above more in the coming lessons, but for now we can think of f sub xx as the concavity in the x direction and f sub yy as the concavity in the y direction. That should be simple enough. We're taking the derivative with respect to x twice, the derivative with respect to y twice. Those are going to give us the concavities in the x and y directions respectively. However, if we're thinking of what's the partial derivative of f with respect to x and then y, well, we think of it as the rate of change of the partial derivative with respect to x in the y. So remember here we are doing, this is saying the partial with respect to y of the partial of f with respect to x. So this is giving us our slopes in the x direction, and this is saying how those slopes are changing as we move in the y direction. So if I have some curve, some surface here, and we have the slope here, then the slope here, then the slope here, and we move then in the y direction along this, we're saying what's the rate of change of these slopes in this way. And then vice versa. So symmetrically, f sub yx is the rate of change of f sub y in the x direction, the rate of change of the slopes in the y direction as we move in the x direction. That's a mouthful. So what we're saying is we have the slopes in the y direction, and if we move then in the x direction, how do the slopes change? Okay, we have a handy theorem for this. Theorem 8.2.1, Clairaut's theorem. Suppose a function f in two variables is defined on a disk D. If f sub xy of xy and f sub yx of xy are both continuous on our disk D, then they are equal. F sub xy of xy equals f sub x. Ooh, typo again. This one's the worst one so far. I'm so sorry, guys. Again, I will have them fixed before you see the blank ones to print out. And I also, forgive me, I am sure it's pronounced, that Clairaut is not pronounced that way. If anyone wants to give me the correct pronunciation, please shoot me an email. One more quick note on partial derivatives before doing more examples is that without getting into a long and formal definition, if we want to take partial derivatives of higher order, we can do so. So if we want third, fourth, fifth derivatives, well, we can do so with respect to x or y, and we can kind of switch. We can do the partial with respect to x, and then y, and then x, and then x, and then y, and then x, whatever we want, right? So we could have the partial derivative of f with respect to x, then y of x comma y. This equals the partial derivative with respect to y of f sub xy, right? Because this is saying first, second, third. So these two xy, we get that first as f sub xy, our first and second. And then this is our third. And we could write this then. So I'm going to actually add a step in here. So f sub xy, this equals the partial squared of f over, we're doing the partial with respect to x first and the partial with respect to y second. And so then when we do another partial with respect to y, that multiplies onto that partial of y right there, and we get a third degree partial on top. So the partial to the third of f over the partial of y squared times the partial with respect to x. Okay, so we can do that as well, and you'll have a chance to practice that in just a few moments. All right, I'm going to go ahead and erase this guy. So, example 8.2.2, find all second-order partial derivatives for f of x comma y equals sine of 2x minus 3y. So, we want to find f of xx, f of xy, f of yx, and f of yy. And we're going to make use of this theorem that as long as we are differentiable on a disk, then these two, the f of sub xy and f sub yx, should be equal, so we can find them both at the same time. Note that the sine function is a continuous function. Its inputs, 2x minus 3y, this is a continuous function in x and y. There's no weird non-differentiable places here. This is just a plane. It's nice and flat. Its derivatives are different in different directions, but it is still differentiable everywhere. The sine function is differentiable everywhere, and so our function is differentiable everywhere. We have no sharp points. We have no domain issues. We got nothing to worry about, so we are able to make use of Clairaut's theorem. Okay. So let's start by finding the first derivatives, f sub x. And you're going to see the book do this all the time. We shorthand and just imply that this is of x and y. This equals, the derivative of sine is cosine of 2x minus 3y. And then we're going to go times the partial derivative with respect to x of 2x minus 3y. This is just 2. Right? The 3y is thought of as a constant. The derivative of 2x with respect to x is just 2. So we get 2 cosine of 2x minus 3y. Now we want f sub y. This equals the cosine of 2x minus 3y times the partial derivative with respect to y of 2x minus 3y using our chain rule. And this equals negative 3 cosine of 2x minus 3y. All right. Now for our second derivatives, if we want, sure, I'm going to move things around here real quick. I'll do that while it's paused. Okay, so I just wanted to be able to work down here. If I take this derivative with respect to x again, so I get f sub xx, this equals negative 2 sine of 2x minus 3y times the partial with respect to x of 2x minus 3y. So this is just 2 again, so this gives us negative 4 sine of 2x minus 3y. Over here, I can take the derivative with respect to y again, and we get positive 3 sine of 2x minus 3y times the partial derivative with respect to y of 2x minus 3y equals negative 9 sine of 2x minus 3y. Great. Our last one then is, let's do f sub xy, so I take the derivative with respect to x first and then with respect to y, and here we're going to have negative 2 sine of 2x minus 3y times the partial derivative with respect to y now of 2x minus 3y. We know that this is negative 3, it multiplies by the negative 2, and it gives me positive 6 sine of 2x minus 3y. We know that this does equal f of y sub x. We're just going to confirm here. F sub y x, this equals. So here I'm going to take f sub y and take its derivative now with respect to x. So this is positive 3 sine of 2x minus 3y times the partial derivative with respect to x of 2x minus 3y. This is 2, it multiplies by the 3, and again gives us 6 sine of 2x minus 3y. This by no means proves Clairaut's theorem, but it gives us an indication that it's true in this case. The proof, I believe, may be found in the back of the Stewart textbook. You can also Google it. It's probably a pretty complex proof. I have not gone over it in some time, to be honest. All right, let's see. An exercise for you guys. Exercise 8.2.2, given f of x comma y equals 3x y to the fourth plus x cubed y squared, find f sub xxy and f sub yyyy. You guys go ahead and give this a try. Pause the video, work it out, and I will come back and hash it out with you in just a few moments. All right, here I have the solutions worked out. If I'm going for f sub xxy, I'm just going to do the derivative with respect to x, then again with respect to x, and then with respect to y. So f sub x equals, here the x to the first, that just goes away. The y is thought of as a constant, so we have 3y to the fourth, plus, in the second term, the 3 comes down, we get x squared. The y squared is thought of as a constant, so we have 3x squared y squared. I then take the derivative with respect to x again, the partial derivative with respect to x again. I should really be saying partial. It's easy to get lazy and just say derivative, but remember, if we're just saying derivative, we have to think of, is y a function of x or not? And it very well, they could be related in some way. And in fact, we can say that this is z, x, and y are all related. They're all related by this equation, right? So we're taking a partial derivative with respect to x again. Here 3y to the fourth is a constant, so that's going to go away. Here the 2 comes down to give us a 6x. The y squared is thought of as a constant, so it just sticks around. And now I take the derivative with respect to y, so 6x is thought of as a constant now. The 2 comes down to make a 12xy to the first. All right, and then for f sub yyyy, we have f sub y equals, here 3xy to the fourth, the 4 comes down and makes a 12xy to the third, as the x is thought of as a constant, plus x cubed is thought of as a constant in the second term. The 2 comes down and we get 2x cubed y to the first. We take the derivative with respect to y again, with respect, the partial derivative with respect to y again. Sorry, easy to get tongue-tied here, right? The 3 comes down, multiplies by the 12, gets 36xy to the second now, plus 2x cubed, because this y to the first is just going to go away, and 2x cubed is thought of as a constant. Take the partial with respect to y one more time. 2x cubed is thought of as a constant, so that just becomes 0 when I take the partial with respect to y. In that first term, the 2 comes down, multiplies by the 36, we get 72xy to the first now. And that's it. That's all we're asked to do for this problem. All right, last page for this lesson. Our last topic is 8.3, implicit differentiation. Given an implicit equation in 3 variables, it's possible to find partial derivatives with respect to x and y. To do this, we still think of z as a function in both x and y. When taking a partial with respect to x, we still think of y as a constant, and symmetrically, if taking a partial with respect to y, we still think of x as a constant. So here we're looking at the equation in example 8.3.1. We're told to find the partial of z with respect to x and the partial of z with respect to y for y times z equals the natural log of x plus z. So to do this, to find the partial of z with respect to x, I'm going to take the partial with respect to x of both sides, so of y, z, and the partial of the right side with respect to x of the natural log of x plus z. So remember, as we're doing this, z is a function of x, but y is thought of as a constant. Okay? Write that down, it's so important. For the partial of z with respect to x, z is a function of x, and the partial with respect to x of z equals the derivative of z with respect to x, the partial derivative of z with respect to x. Now we can't write just z prime anymore because z prime, we don't know if that means with respect to x or y, so we need to be using Leibniz notation in this case. But y is thought of as a constant. It is a constant for our purposes here. So when I'm looking at this over here, the partial with respect to x of y times z, y is thought of as a constant, z is as a function. So this just stays as y times the partial of z with respect to x equals. Now the derivative of the natural log, as long as it has a variable inside, the variable that we're taking with our partial derivative with respect to, then this is 1 over the input. And then we need to say times, by the chain rule, the partial derivative with respect to x of x plus z. So here we have y times the partial of z with respect to x equals. Here our partial of x is 1. Our partial of z is partial of z with respect to x. We get 1 plus partial of z with respect to x over x plus z. Now this is going to get a little messy. I'm going to reorganize things again. Pause and reorganize. Okay, just gave myself a little bit more room here. It's always nice to isolate what we're looking for. So we're looking for the partial of z with respect to x. I'm going to multiply this x plus z over to the other side and distribute. So I get xy times the partial of z with respect to x plus yz times the partial of z with respect to x equals 1 plus the partial of z with respect to x. Go and feel free to take a little bit more room on your own paper if you want to here, or do it on some scratch paper. I'm going to get the partial of z with respect to x, all of these terms on the same side, and factor it out. So I have the partial of z with respect to x of xy plus yz minus 1 equals 1. I moved this over as a minus on the other side and factored it out. And so this gives us that the partial of z with respect to x equals 1 over xy plus yz minus 1. Great. Now we're just going to run through the same kind of work, but with respect to y. This is actually going to be much nicer for us, so we'll see why here in just a second. In fact, take a guess if you want to look at our equation here real quick. Why is this problem going to be simpler than our previous? So I'm going to take the partial with respect to y of both sides. Yeah, it's not going to be a whole lot easier actually, but that's okay. So now I have to use product rule. Okay, I was wrong. I had a guess. Because there's no y here, I was thinking, oh, this is just going to be 0. But z is a function of y, so we're still going to have to deal with that. And in fact, on the left side, I have to use product rule. So I'm going to have to use the first and the second here. So y is the first. The partial with respect to y is 1 times the second plus the first times the derivative of the second is the partial of z with respect to y. This equals, over here we have 1 over x plus z times, I'm going to do this a little bit faster, the partial of the inside is the partial of z with respect to y. Let's kind of speed things up a little bit here. I'm going to, how do I want to work this? Let's go ahead and move this to the, or I'm going to move this y times partial of z with respect to y over to the right side. So that I get z equals the partial of z with respect to y times 1 over x plus z minus y. So I brought this over and then factored out the partial of z with respect to y from both terms to get this, and now I can divide this over to the other side and get the partial of z with respect to y equals z over 1 over x plus z minus y. And I'm going to go ahead and multiply top and bottom by x plus z to clear my complex fraction real quick. It's nice to get rid of those if we can. So this equals xz plus z squared. I could leave that factored. Either way. 1 minus yx minus yz. All right. And that's it. That's our answer for this example. Last exercise of this entire packet. You guys go for it. Exercise 8.3.1. Find the partial of z with respect to x and the partial of z with respect to y for sine of xyz equals x plus 2y plus 3z. Pause the video. I will be back with you in just a few moments. Alright, so we start by looking for the partial of z with respect to x. I take the partial with respect to x of both sides of my equation, so I get the partial with respect to x of sine of xyz equals the partial with respect to x of x plus 2y plus 3z. On the left, this is going to take us a couple steps. The derivative of sine is cosine of xyz times the derivative, the partial derivative with respect to x of the inside of xyz. We're going to have to use a product rule. And just so you guys know, I'm going to think of that as the first, that is the second. In fact, let's do that right now before I work onto the right side. So on the next line, I have the cosine of xyz times. So here, the partial with respect to x of xy is just y, because x to the first is going to go away. We're leaving that constant, times the second is z. So we have cosine of xyz parentheses yz plus the first xy times the partial derivative of z with respect to x. Okay, equals. On the right side, we had the partial with respect to x of x plus 2y plus 3z. With that, we get 1 is the partial derivative of x with respect to x. 2y is a constant, so that's going to go away when I take the partial with respect to x. And the partial derivative with respect to x of 3z is 3 times the partial derivative of z with respect to x. And that will get carried down to the next line as well. So I went ahead and distributed on the left side the cosine of xyz across the parentheses, across the addition here, to get yz cosine of xyz plus xy cosine of xyz times the partial of z with respect to x equals still 1 plus 3 times the partial of z with respect to x. We move the terms with the partial of z with respect to x to one side. I moved them to the right side. The terms without the partial of z with respect to x to the left side. So we get yz cosine of xyz close parentheses minus 1 equals the partial of z with respect to x of 3 minus xy cosine of xyz. Divide that over to get the partial of z with respect to x equals, on top, yz times cosine of xyz close parentheses minus 1 all over the quantity 3 minus xy times cosine of xyz. Great. We're going to do the same thing similarly for our partial of z with respect to y. We take the partial with respect to y of both sides. The partial of with respect to y of sine of xyz equals the partial with respect to y of x plus 2y plus 3z. For our next line, we get cosine of xyz times the partial with respect to y of xyz equals 2 plus 3 times the partial of z with respect to y. On the left, we use chain rule here, and so I'm going to now take the derivative with respect to y, the partial with respect to y. On the right, the x was thought of as a constant, so that went away. The partial with respect to y of 2y is just 2 because the y to the first is just going to go to a 1. Okay, so on our next line, cosine of xyz times xz plus xy times the partial of z with respect to y equals 2 plus 3 times the partial of z with respect to y. Again, I had xy as the first, z as the second, and used product rule on that. All right, I'm now distributing the cosine of xyz. So on the left, I get across my addition. So I get xz times cosine of xyz plus xy cosine of xyz times the partial of z with respect to y equals 2 plus 3 times the partial of z with respect to y. We then move the terms with the partial of z with respect to y to one side and factor it out. The terms without partial of z with respect to y to the other side. We get xz cosine of xyz, close parentheses, minus 2 equals the partial of z with respect to y times the quantity 3 minus xy cosine of xyz. And our final line now is partial of z with respect to y equals xz cosine of xyz minus 2 all over the quantity 3 minus xy cosine of xyz. That's it. That's our lesson for today. Thank you guys so much for listening, and I will see you in the next lesson. Have a great day.